Hello everybody. Today we are going to make an AC analysis. We are going to also have a look at a BJT, how we can use a BJT in Ngspice. Also we are going to make an AC sweep. We are going to change the frequency of the AC signal, and we are going to look at the output, how it is reacting, changing, how it is reacting to changing the frequency. Again, sorry for my English. I am not very good at speaking in English. Sorry for that. Let's get started. I have drawn a circuit. Here we have a circuit. We have a sinusoidal wave voltage source, we have a DC voltage source, we have a BJT, we have resistors, we have capacitors. Also I named the nodes. I'll call here for example N2, here NB, N1, etc. You can name whatever you want. You can call here NC, NB, NA, ABC, or doesn't matter. Let's make this circuit. I have already made a circuit, but I am going to delete it, and I am going to make circuit again. I am going to use BIM. BIM is a text editor. You can use on terminal, and our circuit is here. Let's say BIM. Let's call this circuit 3. Not sure. I am going to get rid of this $sign, so set no list, and we get rid of from it. And the first line is titled circuit 3. It's an amplifier circuit, amplifier with BJT. And let's get started from here. We have V2 voltage source. V2, it is between N2 and 0, and it is a sinusoidal wave. It is a sinusoidal waveform. And here we can see a parameters here. 0, the first parameter 0 is for DC offset. We don't have DC offset, and it is 0. And the second parameter here is 10 milli, which is peak value of the sinusoidal wave, and it is 10 millivolt. Not peak to peak, but peak. Peak to peak is 20 for this circuit. And we have 1 kilohertz frequency. The third parameter is frequency. So let's type them according to this one. This should be 10 milli, 1K. And we have a C3 capacitor between N2 and NB, and it is value 47 microfarads. We have R1 resistor between N1 and NB. Its value is 80 kilo ohms. R2 resistor, NB, ground. I am calling ground as 0. I did here as well. This value is 20K. We have a voltage source here, DC voltage source. It is between N1 and ground, and its value is 5 volt. And we have our C here. Let's type it as RC. It is between N1 and NC. It is value 5K. And here we have a transistor. Let's have a look at the user manual for transistors. Chapter 8 talks about BJTs, and we have seen the general form. The first node is collector, the second base, the third is emitter. I called this node NC, this node NB and NE. So we are going to first type this node because it's collector, and then this node and this node. You don't have to call this node NC. You can call it N1, N2, A, B, C, doesn't matter. But in typing here, you are going to first type collector. So this can be N5, N6, doesn't matter. It doesn't have to be NC. So let's call this Q1, Q for transistor BJTs, and M for MOSFETs also. I'd like to mention it. NC, NB, and NE. And let's say it is mode 1. Let's call it mode 1. What we didn't mention here, these ones. So let me type them. NE 0500, and we have C1 capacitor. This between NE 470 microfarad, and we have C2 capacitor. It is between NC and output. NC, and I am calling this not output. Okay, it is value 470 microfarad. And now we are going to specify the mod 1, which we wrote here, and I am going to found it from internet. So let's type Ngspice model of BC 140. I want to search it with Google, and I found it from this website. Let me show you. Bipolar transistors and general purpose. Here we can see BC 140. I have already downloaded it from it is here, but I'm going to download it again. Let's save it and let's open it. You can see there is information here. What we are going to take here is those lines, that model. Let's copy it and paste it to our circuit here, and we are going to change this. We call it mod 1, remember here, and nothing is going to be changed here. Let's end this. You can search for these parameters from datasheet, but it is going to take a while. It is going to take a lot of time. Somebody puts Ngspice model of the BJT and we are using it. It is the easier way. Take it. Let's close this page and let's close this. Let's close this also. Our circuit is here, and I am going to open a new tab here, and I am in the same directory which contains this file here, which we wrote here. Let me zoom it so you can see more clearly. Ngspice circuit 3.0, and our title shows up here. We don't see any error message. That's good. Let's make a transient analysis. Again, I would like to mention that I'm not going to did I mention it? Maybe I didn't mention it. I am not going to look at the initial conditions. I am going to look at the steady state response, which means when it reach when the time reach infinity, all the initial conditions are not going to have an effect on the circuit. But if you want to include the initial conditions, I showed it from the last video. I showed it in the last video. We are going to type IC of the initial conditions. Let's call the initial conditions of the capacitor is 0 volts. Let's say this, and here transient, the sample rate 1 micro, the finish time, let's go 5 milli, and let's say it starts from 0. I made the finish time 5 milliseconds because this voltage source has 1 kilohertz frequency, which means the period is 1 millisecond, and if we look 5 milliseconds, we are going to see 5 periods of wave. And if I type use initial conditions, it is going to use the initial conditions. Let me show you what is going to happen if I type use initial conditions. It take 5021 data. Let's plot this node N2. Let's plot N2. Here we have 10 millivolts peak voltage, sinusoidal voltage. It is frequency is 1 kilohertz. It's normal as we expected. But let's have a look at here, this node. We have a resistance here. We have a capacitance here. Let's make a superposition and ignore this. We have just this one, and this capacitor is going to be charged in time, and the tau value is R1 times C3, which is 47 micro times 80 kilo ohm, and it is in milliseconds, as you can see, and this is going to affect the output. Initial conditions are going to affect the output because we type 5 millisecond finish time, which is the time this capacitor is being charged. So let's have a look at the NB. We are going to see it plots NB. Here, the capacitor is being charged. As you can see, it is being charged, and it is going to reach some value. What I am talking about, when this capacitor is fed with this DC voltage, and after that this is going to be same, and we have a DC offset here and we have an AC signal here. Let me show you. Let's make 1001 millisecond and start from 1000 millisecond, 1 second, and 1 second and 5 milliseconds. The finish time 1005 milliseconds, the start time 1000 milliseconds, and use initial conditions. and let's plot NB. As you can see, it is being charged and still it is changing a little bit. Let's make this a lot more bigger. It's calculating initial conditions as well. So when the times goes infinity, as you know, this is going to be on steady state. Come on. It's taking a while. That's it. And if I don't use initial conditions, which I type here, it is going to ignore initial conditions. It is going to assign the final values, and we are going to make a steady state values, and it captures. Let's plot NB. Here it is not changing, we can see it. And what I would like to do is here, I don't want to type, I want to type 10,005 milliseconds to see the steady state response. I don't want to calculate the tau value and type here a value according to these tau values. I just want to ignore initial conditions. I want to make the I want to look at the steady state response. So I am not going to use initial conditions. Let's 5 milli pattern 5 milli 0. And it gives an error. I tried again and it captures data. When I first hit enter, it gives me an error, and I tried it again and make the analysis. So let's plot NB again, and we can see this is the value when this capacitor is being charged. So let's have a look at the output. Here we can see the output. I think a little bit saturation happens here. I created this circuit. I didn't get this circuit from any book, so it can goes to saturation. Doesn't matter, you know the basics how to calculate it. And also I would like to talk about this. Let's plot NC. NC has a DC offset, as you can see, and we are eliminating this DC offset by this capacitor, and we are taking this output. Some Ngspice programs doesn't allow you to capture this output because this is floating. They are going to say, hey, this output node is floating and you cannot capture, you cannot analyze the circuit, you cannot make simulation. Ngspice allows you to do that. You can have a node which is floating. This is very good. This is very good. So we know the basics, we know how to do this. Let's look at how we can make an AC sweep. And we are going to change this sinusoidal to AC. We are going to write here AC. This is going to be AC, and its value is 10 millivolt peak voltage, and we are pardon, we are going to make an AC sweep. Let's simulate circuits. We don't have any error, that's good. AC for this one, let me show you from the user manual. Here we can see AC small signal AC analysis, AC deck ND F start F stop. The deck stands for decade variation, which we are going to use for our example. You can also octave variation and linear variation. We are going to use decade variation, logarithmic scale, and ND number of points per decade. We are going to call it 100, and F start the start frequency and F stop stop frequency. Let's make this deck and 100 for per decade, and let it start from 1 Hz and let it goes to 100 megahertz. Yes, again when I hit enter it gives me an error due to the I think initial condition, and I tried again and it captures the data. So let's plot output according to the frequency of the input voltage. And here we can see, as you can see, in 1 Hz it is here, and when the frequency increases, the gain increases as well. As you can see, the peak gain is here, and you can calculate the F cutoff frequencies which belongs to 3 decibel below, or you can look here, it is approximately 670. You can divide it by square root of 2 and you can find the cutoff frequencies, which will be here I think. And as the frequency increases, the gain decreases as well from here and here. We did our circuit 1 kHz, it is here, it's in the maximum frequency. You can make a frequency analysis like that, it is easy. You can do it for other circuits. You can have inductance, capacitors, you can analyze filters, you can analyze passive filters, you can analyze active filters, but I didn't show you how to use op-amps. I am going to show you how to use op-amps as well in the next tutorial. So that's it. Goodbye. Take care of yourself.